Hello and welcome to my article presentation for knot theory. The article that I decided to stick with was the Unknotting Unknots. Uh, and after researching this quite a bit, I found that there are a lot of articles that are really concerned with this same idea. And the underlying question for this article and a lot of others like it is given a complex diagram of the unknot. So not just our trivial one. Can we start to pin down the number of Reidemeister moves that it'll take to transform that given, some people call it a nasty unknot or a hard unknot, into the trivial unknot? And what we're really going to focus on is narrowing that down to give us an upper bound of the number of Reidemeister moves. So for this, we need a couple different representations of knots. And we'll need to kind of understand some key elements from those in order to get this done. So the first one is called the arc presentation. It's a knot diagram that has these horizontal and vertical lines. This first one is just the unknot. Obviously, there's no crossings. This one is actually the trefoil knot. And the thing you'll notice about it is that all the vertical wherever there is a crossing, sorry, let me rephrase that. Wherever there's a crossing, the overcrossing is contained by a vertical strand, and the undercrossing is from the horizontal strand. Okay, that's the main rule of the arc presentation diagram. And kind of heavily related to that definition is the complexity of a knot. So when dealing with the complexity of a knot, it's all about the number of vertical arcs that you find in your diagram. So, we think of the unknot as being a pretty trivial knot, at least the trivial representation of it. It still has complexity too. So that's kind of our goal. That's what we want to get to. We want to get to a knot that has complexity too, at least in the arc presentation. The trefoil has, at least this arc representation of a trefoil has complexity 5. There are 5 vertical strands. And this knot over here, kind of a weird look at it, but it is the figure 8 knot. And it has 1, 2, 3, 4, 5 as well. Well, 6 complexity. And the reason we denote this with a C of L, obviously C for complexity, L kind of stands in this paper a lot of times for the arc presentation diagram of the knot. So not using K, and L not really standing for length, but standing for the arc presentation. Couple of important facts from this. The first one, the very first proposition, and these are going to be mixed up as propositions and lemmas and theorems, but every knot has an arc presentation. Okay, that's pretty big thing, that you can take any knot and put it into this form. I will tell you, after practicing this quite a bit, it can be difficult, but you can always find an arc presentation of a knot. And then the second fact here, just that two arc representations can be two arc representations of the same knot can be related by a finite sequence of some certain moves that we're going to talk about in a little bit. Last thing, really focusing on arc presentation, is that the number of terms, when we look at the number of terms of this summation that deals with the complexity, tells us that number of terms is less than or equal to this summation, and that just has to do with looking at every arc presentation on your way to your I guess on your way from your nasty unknot down to complexity 2. That's why we start with 2, because that complexity 2 is going to give us the unknot. That is the number of terms of that sequence, or sorry, that series. those arc presentation moves that I talked about, we have two of them, kind of three of them. We're only going to be focusing on two because of a pretty easily discovered fact. We're going to deal with destabilization. So that would be like taking this arc here, which looks like a Reidemeister 1 move, and that's because it is. Takes this arc presentation from, this form to this form. That's a destabilization. Also, this one that we don't really, in what we've talked about, we don't really have an issue with this, but in terms of complexity, we do. We notice that this destabilization is going to lower. It will lower the lower the complexity of the arc presentation by 1. So anytime you destabilize, notice here I've got 2 vertical strands. It turns it into 1. Same thing here. I have 2 vertical strands, turns it into 1. The stabilization would increase it by 1, and so we're not going to focus on that. The second type of move is an exchange move, and it takes an arc presentation that looks like this and turns it into something that looks like this. To kind of generalize what we have kind of seen this as, it's kind of like a Reidemeister type 2 move. That's what it looks like on the face, but since there's all these vertical strands, and we're talking about the number of Reidemeister moves, it's actually a combination. You would take a type 2 move here, and then in order to pass this strand through this crossing, this would be a second move, a Reidemeister type 3 move. So those moves continue on down the road until you get to here. Now, the one thing you'll notice about this exchange move is it's not going to do anything to the complexity, but it might, it will, it'll affect the crossing number by either adding 2 to the crossing number or subtracting 2 from the crossing number. So that's a pretty important fact there. And mainly because we want to be going this direction to lower the crossing number. Obviously, we want crossing number of 0 and complexity of 2 to get ourselves to the unknot. The third theorem, the third kind of key fact that we have, and these are the numbers from the article itself. I just kind of group them with kind of their best fitting places. It says that if L is an arc presentation of the unknot, then there's a finite sequence of exchange and destabilization moves that takes whatever arc presentation you have, takes it to the unknot. And that's kind of that same idea from the previous page. The big lemma that is shown in this article that is important is that it takes no more than n-2 Reidemeister moves to perform an exchange or destabilization. If we look at destabilizations, it really only takes 1 Reidemeister move. So that's definitely less than n-2 because our complexity is going to be at least 2. In fact, it's only going to be 2 when we get to our unknot. So if this is our last move, our complexity would be 3. We might have something like this, and we're going to destabilize that to give us our unknot that we want. And then the exchange moves, like I said before, it takes quite a few moves, but it turns out that that exchange move does fall into that category of less than n-2, given n as the complexity. Another type of knot diagram that we're going to work with is called Morse form, and it's just another way to visualize a knot. It has a bunch of rules, and I actually emailed one of the co-authors of this paper to get a little better idea of what Morse form really is all about. And what I was told was basically think about the knot on the coordinate plane with respect to the vector 0, 1, or think of the positive y-axis as my given vector. And then I can have no arcs that are perpendicular to the vector, so I can't have any horizontal lines. I can't have any inflection points. There's at most one singularity at each height, so all these kind of cusps have to be at different heights. And then each crossing, and this was the big one for us, was each crossing is oriented with a 95-degree angle to the given vector. So all these arcs have to essentially have slopes of plus or minus 1. Then kind of one of the other big things that's covered is the maxima of a Morse diagram, or we can think of the number of maxima. That's kind of what we're looking at here. And it's just kind of how we think of it back in calculus, the number of local maxima of a knot. In this case, there's these two right here that you think about a neighborhood around the point, and I mean I'm sure you could get to sigmas and deltas if you want to. I don't really feel like it here. So then the lemma 2, which is another really big lemma for this main theorem that we're going to get to, is if we have so many crossings, CR of the knot crossings, and the number of maxima BK, then there's an arc presentation. So we're going back to arc presentation that has complexity equal to, so given this one, this is actually the Morse form of the trefoil. And there is an arc presentation of the trefoil that has complexity double the maximum, which is 4, and the crossings, there's 3 crossings. So there is one that has 7 as its complexity. There's a representation of the trefoil that has 7 as its complexity. One of the big theorems that this paper covers is an upper bound on the crossing number. And it says that suppose K is a diagram in Morse form of the unknot with crossing number CR of K and number of maxima B of K, then for every I, and we'll get to these I's in a second, the crossing number of that knot, that ith knot, has to be less than or equal to capital M minus 2 squared, where M is the double the maxima plus the number of crossings that we just talked about. So the number of crossings has to be less than that minus 2 squared. And that's a pretty big result that's talked about in this paper. And that ith form of K is in this sequence of knots where every Ki, or it says here that Ki plus 1, is obtained from a single Reidemeister move being done on Ki, and then our ending knot is the trivial representation of the unknot. So that gives us an upper bound on the number of crossings, but what we're really going to focus on is the upper bound on the number of Reidemeister moves. So the theorem, the kind of keynote theorem of this paper, is if we have a diagram in Morse form of the unknot with the same crossing number and maxima, and we still let that capital M equal double the maxima plus the crossing number, then the number of Reidemeister moves required is less than or equal to this sum, which is a nasty sum, but it definitely comes from some of those previous lemmas and and propositions that we covered. So just to kind of highlight the proof of this, if we let K be an unknot with a non-trivial diagram, and we consider L sub K to be an arc representation, of that knot K, then we know that the complexity of that is, or we say that the complexity of that is n, for some n. It has to be, again, greater than 2. We know that there's no more than m times n minus 2, so that n minus 2 Reidemeister moves came from our previous page, and there's m of those n minus 2, the upper bound of n minus 2, there's m of those from that number of terms of all the different kind of stages of your unknotting process. So since m is less than this, we can bring that into our equation here. So that tells us that the number of Reidemeister moves still has to be less than or equal to, and we kind of just combine those. So we've got this sum here and the n minus 2. We've substituted this m with this sum, and that came from all the terms of the knot, from the nasty version of it all the way down to the trivial unknot. So we get that it's less than or equal to that, which lastly, since the complexity has to be less than that capital M, and it has to be less than the capital M because n is the the starting complexity. Since it has to be, obviously, if we're trying to uncomplicate this knot, we're trying to unknot this knot, we're trying to turn complexity into 0, n has to be less than that starting value. That tells us that the number of Reidemeister moves to unknot our unknot has to be less than that same sum. All we do there is we replace this lowercase m with our capital M, which was our double the maxima plus the crossing number. So kind of a complicated theorem, and it turns out that this does not give a great upper bound. It's actually a pretty large upper bound, even for the paper goes over a knot with 10 crossings, and noting that it takes 12 Reidemeister moves, or it takes 12 different 12 different pictures to get from one to the other, just from 10 crossings, and they obviously get it done in 12, but this formula gave an upper bound of somewhere in the 300s. So it's not a great, I mean, it's a great result, but it's not a real finely tuned machine to figure out the exact number of Reidemeister moves needed. One of the biggest issues we get is when we have those crossings that look like Reidemeister 1 moves, and we want to pass that whole loop through. When we want to pass a loop like this through this other part, and we have to do a type 2 move to bring each one of these loops down, and then a type 3 move to bring it through the crossing, just like we saw in that exchange. That's what really that's what really factors into giving this upper bound, and why this upper bound can be such a large number in relation to what it might actually take to unknot the unknot. So hope you enjoyed, and we will see you later.